In this video, we're going to discuss free body diagrams and how to figure out the loading at a given cross-sectional area of a part. So let's just consider some beam. And suppose we've done some sort of loading on this beam. Maybe we have a force acting down on this beam. And maybe we have a support underneath a couple places in the beam. Up until this point, we've been considering stress states. So if I take an infinitesimally small location within the beam and look at it in a larger scale, we would draw some sort of stress cube, and we would recognize that there are some stresses and maybe some compressions. We don't really know all that's in here, but we'd be able to express it as some sort of sigma x, sigma y, sigma z, tau xy, tau x z, tau yz. And this would be our stress tensor of how the conditions are loaded within this infinitesimally small block. So the next question we need to ask ourselves is, with a given loading condition, how can I calculate what the individual elements of the beam are experiencing? Okay, so there's several different methods to do it. In this lesson, we're going to be discussing using the free body diagram as a method of actually calculating what the stresses are. And maybe as a comment going into it, my first analysis is going to be a fairly simple one. What we're going to be doing is considering this beam to be identical in the third dimension. In other words, I can express the beam maybe something more like this. Okay, you've probably seen something like that. We've got some reaction forces here and maybe some load. We'll call that F for now. We'll call this R1 and R2. And now again, what I want to be able to define is the loading that's occurring at every location in the direction of the beam. Let's go ahead and give it a coordinate system as well. We'll call this direction X, this direction Y, and we're going to assume that everything in the Z direction is the same throughout the whole beam. In other words, this isn't really a force, it's really kind of like a load of forces across this line, infinitesimally small in width, but spanning the whole distance. Okay, so there's kind of the background of where we're going. The first thing I can do is just calculate what these reaction forces are for a given force F. And what I'm going to be using for this entire analysis is basically two of Newton's equations, Newton's second law. One of them is the sum of the forces in the y direction is equal to 0. Okay, so that gives me an equation. For instance, in this case, R1 plus R2 minus F is equal to 0. Let's write that R1 plus R2 minus F is equal to 0. Okay, and the other set of equations that I would be able to use, or the other motion equations, is the sum of the moments about some point. Let's say x is equal to 0. So let's call this point right here my x is equal to 0 point. And we'll set that equal to 0. And we learned previously, hopefully this is review, that you can sum moments about any point. We're going to choose to do it about 0 just because there happens to be a force that runs through that. And we know that moment is force times distance. So let's say this distance for now is A. And then the length of the beam is B, and this reaction force is at the other length. So now I could say F times A is trying to rotate the beam this direction in a clockwise direction. So I'll call that negative for now, minus FA. And then R2 is trying to rotate the beam counterclockwise. I'll say that's positive, plus BR2. R1, it doesn't matter because the distance from where we're considering is equal to 0. So this is equal to 0. So now with these two equations, if I know F and A and B, I can solve for R1 and R2. And that gives me the first step. This is just a simple free body diagram of a beam. Okay, so now from here, let's draw a different problem now, and we'll begin to take a look at what happens if I were to slice the part at some distance and figure out what's going on at that location. Okay, so first let's draw a beam, and I'm going to be a little bit more careful now with my grid lines. I'm going to say that this beam is 20 lengths long, 20 long, and it has a force located at 5. And I'm going to say F is equal to 800 pounds. Got R1, R2 are located at either end. I'm going to say the length is 20. And we're going to say the distance to F is 5. One more thing I'm going to do, I'm going to start a coordinate system, and I'm going to call it X in this direction. Okay. Now the first thing we just talked about is using the free body diagram to calculate what the reaction forces ought to be. So I have R1 plus R2 is equal to 800. That's using some of the forces in the y direction is equal to 0. Okay. And by using some of the moments, and let's still use that 0 point around x is equal to 0 is equal to 0. So let's see what that looks like. We've got 5 times 800. This is going to be inch-pounds. Maybe I should give units here for my lengths. This is going in the clockwise direction, so I'll call it negative plus 20 times R2 is equal to 0. Okay. So 20 R2 is equal to 4,000. Okay. So R2 then would be equal to 200, and then going back to my original equation, I'd realize that R1 has to be equal to 600 pounds. Alright, now that I have that, what happens if I were to break the beam right here? So let's consider that where I'm breaking it, we're going to call it X, and what we're considering right now is when X is between 0 and 5 inches. Okay. So when that's the case, let's do a free body diagram of just that part. So I'll show that as the break. I have R1 acting on it, and then there's something happening in here. I'm going to go ahead and draw these directions according to a convention. Okay, so let's talk a little bit about the convention of internal stresses. When we're talking about, so what's happening here is the force F is trying to shear the beam in half. And there's got to be something going on inside the beam that resists that shearing. Okay, so the way that we consider positive, if the left half is trying to raise above the right half, then we're going to consider that to be positive shear, and the other way is considered negative shear. The way we can draw that is if I have a beam, it's got equal and opposite forces inside, and the way I'm going to say it, if it's on the right side of the break and pointing down, that's considered positive shear. Okay. On the other hand, if I have a beam, if we're looking at the other side, the directions are still the same. So again, if I'm on the right hand side and pointing down, that's considered positive. If I'm on the left hand side and pointing up, that's considered positive. So this is positive sign convention for shear. Okay, so I'm going to go ahead and say that I know that there is a shear element here. I'm going to call it V. I'm not sure what that value is yet, but we'll go ahead and label it there. Okay, and now let's sum forces. Let's see, there's another thing that's happening inside here. There's also a moment that's being resisted. And the convention for resisting a moment, the standard way most people have learned it, is to consider if you're making a smiley face, that's positive. So this is positive convention. I would rather say that it's holding water, but however you want to say it. Convex is holding water versus the negative would be shedding water. And again, if I look at this on the inside, if I were to take the break on the inside of the beam, this is also considered the positive. So what that means is right here, there exists a positive moment. I'm going to call it M. Okay. And if we want to, we could even label that these are functions of x. So I'll put a little x as a subscript just to remind myself that these are going to be functions of x. Okay, so with this as my free body diagram from 0 to 5 inches, let me write what I've got. I've got R1 minus Vx. So keep in mind, this is the positive sign convention, but when I do my free body analysis, I'm going to just treat it like a normal force, and pointing down is negative direction. So this is equal to 0. This is my sum of the forces in the x direction is equal to 0. Okay, so R1 is equal to Vx, which is equal to, from up above, 600 pounds. Okay. Now notice that at this point, it doesn't matter where I make the break. Anywhere from 0 to 5 inches, I'll get 600. This is not, at this point, a function of x, as long as I'm within that frame. Okay, let's sum moments as well. So I'm going to sum moments. And again, I think I'm going to sum moments about 0. I don't have to. I could sum moments about x, but it's a little bit more confusing to think of it as a function. I'm going to sum moments about the 0 point here, and I know that that's going to be equal to 0. Okay, so R1 is always going to not be contributing to that particular moment. So I have Vx times x. This is trying to spin it clockwise, so we'll call that negative. And then there's another moment opposing it, and the way I've drawn the sign, it's positive, so plus mx is equal to 0. Okay, so that says mx is equal to Vx times x. Okay, so again, I'm only considering between 0 and 5. Vx is just a constant, so what I'm going to get is mx is equal to 600 times x. Okay, so now I'm going to start writing v as a function of x is equal to 600 for 0 less than x less than 5, and m as a function of x is equal to 600x between 0 and 5. Okay, and this is going to work all the way until I get exactly at 5 inches. Okay, so now let's consider a beam that goes beyond the 5-inch mark, anywhere from 5 to 20. So I'm considering where 5 is less than x is less than 20. And at that location now, let's draw a free body diagram. And I'm going to go ahead and start again with what I know is positive convention, so we'll call that V sub x and M sub x. And now let's see what we've got here. Okay. First thing, let's sum forces in the F direction about x and set it equal to 0. I have positive 600 minus 800 minus Vx is equal to 0. So Vx is, again, it's going to be a constant, and now it's going to be minus 200 pounds. Okay, summing forces, summing moments, and again, I'll do it about 0 just for convention's sake, equal to 0. Okay, we're going to consider counterclockwise to be positive, so we've got 800 times this distance, 5 inches, so 800 times 5 in the clockwise direction is minus. Then minus, let's see, my V of x I've calculated was 200. Actually, this should be positive 200. Let's see here. Let's make sure that works out. No, it should be negative 200. So in this convention, the value of this value is negative 200. So actually, I could have shown it by having it point the other way, but we'll have it point the positive direction from the understanding of how shear occurs. It is in the negative direction of the y-axis, so it's labeled, so when I sum my forces, it's negative. And I need to add the moment and set all that equal to 0. So this is going to say that mx is equal to 4,000 minus 200x. So this is what's happening now anywhere from 5 to 20 inches. Notice v of x is a constant. M is a function of x. So now let's now do a graph. So now I'm going to label this v. So we expect that something strange is happening here at the 5 mark. All the way when x is equal to 0, from the last problem, we saw that this is going to be equal to 600 pounds. Let's say that this is 600 pounds. And then when we get to 5 inches, it's going to drop to minus 200 pounds. So we'll say this is minus 200, that's positive 600. It's going to remain there until we get to the end of the beam. Now let's take a look at what this looks like. At 0, coming from the left-hand side of the beam, as soon as I get inside the beam, there's now a 600-pound shear load that matches this 600-pound load that's occurring in the same direction. Okay. At 5 inches, I go down 600 and then down another 200. So I actually dropped 800 pounds. That makes sense. That's the 800 pounds that's actually applied all the way to the end, and then at the end I'm going to go back up 200 pounds, back to 0, and there's no internal stresses once I'm outside the beam again. Okay, so this is a good description of the shear forces that are happening inside the beam from 0 to 20 inches. And if I was concerned about failure, I would expect that it's going to fail in this 600 regime right here. Let's do the same thing with the moment. So this is m. Here's my x-axis for m. And I expect something to be happening here at the 20 mark. This is the 5 mark. I'm expecting something strange to happen there. And there's going to be something happening at the beginning here. Okay. This equation right here, this was for 5 less than x less than 20. Just so that we can remember it, let me write mx was equal to 600x for 0 less than 5 less than x less than 5. So let's look at this first section here. When x is equal to 5 inches, I'll go all the way up to 3,000 pounds. When x is equal to 0, I'll be at 0. So here's the 0 point. At 5, we would be up, let's say this is 3,000 up here. And it's a linear line. It's a linear curve between 0 and 3,000. Okay, that's going to take me up until this point. Now let's see what happens if I plug 5 inches here for this one. 5 inches times 500 would be 1,000 pound inches. 4,000 minus 1,000 is equal to 3,000. So I still get to the same point from the right-hand side. And then if I were to plug in 20 inches here, 20 times 200 will take me back to 4,000. 4,000 minus 4,000 is 0. And it's a line with a negative slope of 200 pounds per inch or pound inches as we come down. So this is what my moment diagram looks like. Maximum moment occurs right where the load is at 5 inches. And so if I was concerned about failure for this part, the most dangerous place for the part to fail is going to be this location just to the left of the load where I have the maximum moment as well as the maximum shear. And what we'll be doing as we go further is, now that we know shear, maybe there's some sort of formula that I can understand of how shear relates to the stress that the parts are going to feel at this cross-sectional area. So we'll begin to look at that cross-sectional area. So this is the free body diagram analysis of how to make a loading diagram for a given loading condition.